We're also going to divide it up into two parts. So when it comes to the lab report for this experiment, you will do one lab report for both parts. So it'll be combined into one big thing. So the due date is much, much later because we have to do both parts. The first week, what we're going to go through and do is determine the rate law for a particular reaction. So if we're going to decide what's happening, it's the rate law for iodide reacting with hydrogen peroxide. So at minimum, what would we need to put in our little reaction? Iodide and hydrogen peroxide. Okay. Is that all that goes in there? No, there's a whole crap ton of other things that go into your individual reaction. They all have very particular reasons behind why they go in there. All of that is introduction material. Okay, you need to know why we're doing each of those steps. So you have to address each of those particular reasons. So when it comes to the report, you've got your abstract. We're adding the abstract now as an extra piece, your introduction, and then the results and calculations. Okay, so this one is a pretty big report as far as what things you've got to put together. Okay. Your abstract, because I didn't create a slide on this yet, what should show up in your abstract? We'll break it down into individual parts. The very first part would be, any ideas? What should you start your abstract with? A very clearly stated goal. So for part one, it's determining the rate law. For part two, we're looking at activation energy. So you would need to come up with a succinct goal that summarizes both parts of the experiment into ultimately one sentence. All right? Next part of the abstract, which is usually included in with the goal at the same time, so that your first sentence or two usually are a bit long, would be to state kind of a how. So what experimental conditions are you doing? Are you using anything special to watch the reaction? That kind of stuff. The next part would be your important results. This one usually gets a bit vague. Some students like to include a whole ton of results. And one of the abstracts I think I've seen before is someone summarized all the different volumes of solutions that they added into their reaction in the abstract. That is not a result. What is your result of the part one? It's your rate law. Rate equals K times your I minus to whatever power. You'd have to specify what that power is because your abstract is supposed to say what your result is. Times your peroxide to its power. And again, specify that number. Okay? What's the important result of the second part of the experiment? Your activation energy for the reaction. And officially, though I probably won't grade for it, the A value, your orientation factor from your Arrhenius expression. Both of those things you will be able to conclude or determine in the course of that experiment. Okay? You should include any kind of error associated with these numbers if you have that error available. If you don't have the error, then don't worry about it. I don't know that we're going to see a whole lot of error show up in this report at all. That would really push into the discussion and conclusion. We aren't going to put an actual number error on anything we do. Okay? The very last part of the abstract was your experiment a success? Was it not? Okay? Success is a vague term. Who gets to determine the success? You do. You're the one that ran the experiment. You get to decide whether the experiment was successful or not. Okay? So if you got activation energy or an A value and you were able to find out what that was supposed to compare to, and it's very, very close, you could come through and say, yes, the experiment was very successful because we got a number that was actually accurate. Okay? if your number is way off, okay, or you have no way of evaluating it, how do you determine your success then? Well, did you learn anything by doing all the calculations? Hopefully, yes. So you could say it was a successful experiment in improving understanding of rate or kinetics for this particular reaction. It doesn't have to be correct per se, but you did improve your understanding of the kinetics. Okay? Or it could just be as simple as, yes, we now understand how to use burettes properly. Okay? That success sentence is something that needs to show up in the abstract, but it can be whatever you want it to be, as long as it's relevant to the experiment. Don't tell me it's a success because you woke up. Right? It's not particularly helpful. Okay? We'll then go through and do the introduction. Again, remember, this is where you summarize everything that you knew prior to going into lab. So any solution that you use, you need to know why you're using it, what its involvement is in the reaction. Okay? Are there balanced equations that you should know? Okay? Are there important equations that you're actually going to use instead of looking at a reaction equation? Are there important mathematical equations? Those need to get discussed and introduced in the introduction. As far as your results and calculations go, when we pull up the Excel file, I'll show you what I would expect to see as far as the results go, and I'll attempt to show you what's going on with what calculations need to show up as well. We'll probably have to do that next week when we start part 2. Okay? So we can get a little bit more information in there to decide what shows up, what doesn't. So, introduction. Ultimately, we want to break our introduction into kind of 3 main ideas: a why we're doing the individual experiment, how we're going to approach the experiment, and then are there any complications with the experiment as we go through and do it. Okay? So why? Why do we want the rate law for an experiment or for an individual reaction? Well, if we're going to try and predict this reaction in a different environment, it might be nice to know some information about it. Okay? If we came in and told you that this experiment was going to take an hour to go beginning to end versus it's going to take 4 days, is your mood going to be changed depending on that time frame? Probably. If you have to spend 4 hours in the lab as opposed to 1 hour, or 4 days sitting in there waiting for the experiment, you're going to get a little bit irritated. Okay? So that predictive power, knowing some information about the general reaction, is important. Okay? For this first part, what we're looking at is a rate law. So what we want to do is introduce a couple terms, or a couple ideas. First, the balanced equation. What equation are we actually studying the rate for? So that's what we've got written up here at the top, or our first equation. Whoa. Shoot, sorry. This first equation is ultimately the reaction that we're studying in this case. So we're going to take iodide and react it with peroxide. So what we want to do is monitor this reaction and determine some rates from it. We could also come up with a general rate expression for this. What would our rate expression be? Well, we know rate is equal to, okay, good, our rate constant times concentration of our reactant, so iodide, to what power? X, good, we don't know it at this stage in the game, times concentration of peroxide, to what power? Y, again, we don't know it. Okay. So, can we translate our coefficients across? It's a really good question to ask. Okay, we cannot do that in kinetics. Equilibrium, we're allowed to switch those coefficients across. In kinetics, our coefficients must be determined experimentally. There's 2 ways they can be determined experimentally: doing all the calculations with all the big fancy numbers, or you're given a mechanism where you're told that this is an elementary step. We don't have that information. Okay, so we have to go through and predict those calculations. We do not know what those orders are. Yes?
Is there a reason that first equation isn't balanced?
What? Oh, yes. I forgot. I copied it from the lab manual, I thought. It's not balanced in the lab manual either. Why is it not balanced? There's a couple things going on with it. The primary reason is a redox reaction. As we'll find when we get into chapter 18, redox reactions require a little bit more difficulty in the process of balancing the equation, right? And that's what this acid solution is for. Okay? So that acid solution is ultimately telling us that we need to add water and acid accordingly to balance out the equation. We'll worry about that when we get into chapter 18. This term, saying that it needs to be in an acid solution, is going to become really, really important for us. Okay? As far as what's occurring in the reaction, we still only need 2 iodides per 1 peroxide. Okay? That's where our oxidation is going to go. Did I miss something else?
Oh, no, but you just added 2 water to that.
The exact locations on where you add the water and the hydrogen ion differ, and I'm not smart enough to look at it fast enough to solve it right now, so we won't worry about that. Yes?
Sorry, you may have answered this, but is it supposed to be, so on the lab manual, the equation's different because there's water at the end.
Did they balance it in the lab manual? I thought they didn't.
It doesn't look like it is, but there's different.
Which equation are you looking at?
Equation 3.
This is equation 3.
H2O at the end in the lab manual.
Oh, sorry, that's H2O. That is a typo. You're absolutely right. That should be water. That might be why you were pushing more towards balancing. So yeah, there's more stuff that has to get added to this to completely balance it. That information is in this acid solution stuff. It's officially not as balanced as it needs to be, okay, to be 100% correct. That acid solution is important. We will see that later on in the semester when we look at redox reactions. This is a redox reaction, which makes the balancing a little bit odd. Okay? In acid solution, since we're now on that topic, if it says it's in an acid solution, that means the reaction needs to be acidic. What happens in the course of the reaction? Something's going to react with that acid, and our acid now is no longer present. Is that going to change the rate for the reaction? If it needs to be acidic, and we stop it being acidic, does that change it? Yes, that will change the rate for the reaction. So one of the things that we would need to make sure that we account for when we go through and set this up, which would be kind of in our how category, which isn't on there, is we need to have a buffer. We need to put something in there that's going to stabilize the acid concentration and make sure it doesn't change through the course of the reaction. Okay? So that almost actually kind of worked as a reasonable segue. We need to have a buffer because our balanced equation suggests that we need acid present. Okay? If we get back to the how, what we're going to have to do is mix our reactants. So we can mix iodide and peroxide in varying concentrations to generate our table. Remember when we solved for orders in lecture, we had rates, bless you, we had concentrations of our reactants. So we can mix these in varying concentrations and monitor the rate of the reaction. Okay? Problem, we need to visualize this reaction. How do we know it's actually occurred? So we could look for a color change. Iodide does happen to have kind of a nice purple color, but it's not an instantaneous thing. Okay? As we slowly increase the concentration of iodide, we might see that color. So deciding exactly the instant when we have iodide is not going to be easy. Okay? So what we need to do is add in some other kind of indicator that allows us to see this color change immediately, or the presence of iodide immediately. Okay? One of the key reactions available to us is that iodine in the presence of starch will turn blue instantly. Okay? So it's a very, very swift color change. So what we're going to do is now not only add iodide, peroxide, and a buffer, we're going to add starch. Okay? So now we get all these things mixed together, and what happens? The iodide ion reacts with peroxide to form iodine. Iodine then reacts with starch, color change. Yay, stop the reaction because we now know that iodine has been formed. Okay? What's the problem with that? To determine a rate, we need two things. We need concentration and we need time. This reaction actually happens relatively quickly, which means pretty much as soon as we mix them, we get iodine, which means as soon as we mix them, we get blue. How fast are your reflexes? Okay, not very good. Okay, so hitting start and stop, okay, we're now adding an extra feature, an extra problem to this reaction. Now it's not just the reaction occurring and doing the starting and stopping, it's also the dynamics of your hand. How fast can you respond to the start and the stop? That's an error we want to minimize. So what we want to do is have the reaction take much longer so that if we have a start-stop issue, that percent-wise makes a minimal issue, okay, in our calculations. Does that kind of make sense? So what we need to do is now also incorporate a delay factor. The color change will give us that time, but we need a delay factor. Okay? That delay factor is our complication, okay? Or one of our complications. What we're going to add now is a species known as thiosulfite. Oh, thiosulfite? I might be saying it wrong. Thiosulfate, okay. S2O3 - 2. Okay, that complex ion. That ion reacts very, very rapidly with iodine. Okay? So as soon as iodine is formed, before it can react with the starch, it reacts with the thiosulfate. What happens to the presence of iodine? No longer there, because it's reacted with the sulfate. Okay? Well, if it's no longer there, do we see a color change? No. So what we can do is add in the thiosulfate to prevent the reaction from actually indicating the presence of iodine. We know this one's still going to progress forwards to form iodine. Iodine very rapidly reacts with our thiosulfate, go back to iodine, or iodide, okay, and the non-reactive form of our sulfur compound. When would it actually form our blue color? We need iodine for it to form blue. But iodine immediately reacts with the thiosulfate. When could we see that blue color?
Just to let you know, it's sodium thiosulfate.
Okay.
Okay, was it?
That's why I've been saying thiosulfate.
Okay.
What happens if I don't add any thiosulfate? When do we see the blue color? Immediately. Let's say we added an infinite amount of thiosulfate. When would we see the blue color? Never, because there's an infinite amount of this. Okay? So how could we set this up so that we can actually see that color change? We will change the concentration of our thiosulfate. And we'll pick a standard concentration, and we'll know that when we see the blue solution, all of the thiosulfate has reacted. Okay, which does two things for us. One, we get that delay factor, so now we can actually time. The other thing it does for us, to get a rate, what do we need? Concentration over time. We now have the time, how do we have the concentration? We don't have the thiosulfate, how much iodine is produced? The indicator doesn't give us a raw amount. That reaction is supposed to happen quickly and deep color change instantly. We don't have a way to determine an amount of that starch iodine complex. However, with the addition of the thiosulfate, can we determine a concentration? When it turns blue, how much thiosulfate is present? None. How much thiosulfate was present to begin with? Would we know that? Yeah, we put it in there. So what we can do is determine the concentration of thiosulfate. Ultimately what we started with and what we end with, which is 0. Okay? At that point, if I know the concentration, that where it's reacted completely, do I know how much iodine was there? If I give you 2 molecules of thiosulfate, how many molecules of iodine reacted? How do you know it's 1?
Coefficient.
Balanced equation. We can convert the concentration of thiosulfate into iodine. Okay? So our thiosulfate gives us 2 things. It gives us that delay factor, and it also gives us the concentration of iodine, which ultimately allows us to determine the rate for the overall reaction. Okay? So at this point, we've got iodide, peroxide, buffer, starch, I'm running out of fingers, and thiosulfate. We've got 5 different things going into this reaction just to monitor the reaction of 2 things with each other. Okay? Is that all we end up adding into the reaction? Also add water. Did anybody actually go through to see why we add water? Is the water amount the same in all experiments? No, we vary the amount of water. Okay? One thing I'd ask you to do is go through and look at the total volume for each of those solutions. What's the total volume for each of those? They're all 40 milliliters. Okay? We're adding water to make sure that for each trial, the volume stays constant. Why is that important? Because when we go to determine our rates, what did we need? Concentrations. If the volume is different, what happens? Our concentrations are also different. So what we're trying to do is control as many variables as possible. We have a way to kind of account for a change in volume, but ideally we keep that as constant as possible. We can limit that variable from affecting our overall reaction. Okay? To give you kind of an idea on what's going on with this. What you guys are doing is ultimately what someone probably did for a PhD. Okay? Except when they did it, it took them 5 years to do it. Why did it take them 5 years to do it? Well, they took iodine, mixed it with peroxide, and said, oh, look, a color change. I formed some iodine. How much iodine did I form? Oh, crap, I don't know. So now I need to come up with some way to monitor the concentration of iodine. So let's add sulfate or thiosulfate to it. Oh, now I can monitor the concentration of that. Okay? And they go through and, oh, I'm still not getting good results. What happened there? Oh, well, my pH changed. Okay? Each of these individual independent variables that we're now adding into this equation probably took some poor grad student a year to figure out that that's what was going wrong with it. Okay? Which is a bit painful of a prospect for any of you considering PhDs. But that's ultimately what PhD work turns into. You start with an overall idea of what you want for an experiment that is ridiculously simple. All we want to do is figure out how fast it takes to go from here to here. Really, really simple idea. And what do we have to add to that? All this other junk to control all the possible things that could change how that reaction worked. Okay? It's one of the reasons why science is interesting and why science is difficult. You can come up with an individual experiment and say, yes, I think this works, it's repeatable, and then it turns out that you forgot that you didn't control temperature. Well, now everything's thrown into question. Maybe temperature affects your reaction. So what do you have to do? You go back and redo every bloody experiment. Okay? And now you've got a control for temperature. Then you say, yay, okay, I finally got it all controlled. You submit it out, and someone goes, well, you didn't account for the humidity at the day of your experiment. So you go, well, thanks. I appreciate that information. Now you go back. What do? Repeat all of the experiments again, controlling temperature and now controlling humidity. Okay? So a lot of this kind of research or these experiments that you're going through and doing, someone had to go through and do it first where they tested all of this and saw that everything failed. You're being set up to succeed, okay? Which sometimes bores students because there's now no challenge to it, but also sometimes you kind of get lost in how much information actually went in to make this. Okay? There's a lot of effort behind how these experiments are designed and put together, okay? Just to give you an idea. So let's look at, or questions about that. Okay, so let's move to what you would do in lab. Okay, so what I've got here is what appears to be a big, massive, ugly table. Very, very similar to what your lab manual had or your lab procedure has. I added a couple extra things. You're going to be measuring the amounts of each of these species, your buffer, your iodide, your starch, your thiosulfate, your water, and your peroxide from burettes. Ooh, actually, let me check that. You should be measuring them from burettes. Yes, you are measuring them from burettes that are already in the lab room. Okay? They're not in our lab per se, but if you ever look, there's that door on the far side. If you go through that door into the next room over, you've got a big sequence of burettes. Those are all of these individual species. They're all labeled with concentrations on them. Record the concentrations off of them, because maybe they change the concentrations on us. So make sure that you know exactly what those concentrations are, because those are incredibly important to solving your overall problem. Okay, so your solutions are all in that back room. You'll notice my chart's a little bit different than what you've seen. Because you're reading these off of burettes, you'll have final and initial volumes. Okay? You should officially measure the final and initial. Okay? Whether you do or not, that's entirely up to you. But officially, that's what you're supposed to do. And that difference between those should match what your lab procedure gives you. Okay? They give you that chart with recommended volumes for everything. Your volume should come out very, very close to those. They do not need to be exactly that, but very, very close. So if it says 5 milliliters plus or minus probably 0.2 or 3 is, fine. Okay? So for trial 1, you'll measure out your buffer, your iodide, your starch, your thiosulfate, and your water into one Erlenmeyer flask. Okay? That is now solution A. You'll then measure into a separate flask the peroxide, and that's your solution B. Why do we not drop the peroxide immediately in with everything else? What happens when the peroxide hits the iodide? It starts to react. If you aren't timing when you first mix them, your time value now to determine your rates is wrong. Okay? So you'll set it up as two separate solutions. You can bring them back into the room in here or the lab room. As soon as you mix them, start the time. I would recommend a quick swirl just to make sure they're mixed, and then you just let it sit and do its own thing. We don't want to agitate it too much after that, because we can now start to change pH, introduce CO2 or other features into it. Okay? So again, minimize variables. We do want a quick swirl. Why do we want to mix it real quickly? If you don't mix, what happens? It only partially reacts, and you get weird color changes when you reach the end point. Okay? So you'll mix, make sure they're roughly stirred, or add them, make sure they're roughly stirred with each other, and then just let it sit and time. Okay? So while one person is timing, the other person can start doing trial number 2. So we are doing this in partners. Okay? Make sure that you keep those two solutions separate until you're actually ready to use them. Any questions about that? Next fun part, question right through the middle of this. Anybody know any expected times? How long should these reactions actually take? So the longest one takes upwards of 10 minutes, I believe. The shorter ones take in the 3-minute range. Which one takes the longest? Okay, what you could do is kind of cheat and look at the concentrations of iodide and peroxide in each of those cases. Okay. What happens as we move down through our trials? What happens to the concentrations? The first ones are the longest, the last one is the shortest. Okay. If I remember correctly, I think trial 1 takes about 9 minutes, and then it drops roughly 1 minute to 2 minutes per trial downwards. Okay. So the last trial, trial 5, should be about 1.5 minutes, I think, as far as time goes. Okay? Questions about what you're doing in the lab? Okay? Relatively boring. You burette, mix, time. Okay? So the observations for this experiment, beyond all the data collection there with those volumes is relatively simple. You see blue color or you don't see blue color. If you don't see a blue color change after, say, 15 minutes, what likely happened? You messed something up. What that messed up was, I don't know. Okay? It could very well be that you didn't add peroxide. It could mean that you didn't add starch to it. Okay? There's all sorts of different options of why it went wrong. If you push over 10 minutes, because I don't think anything goes longer than 10 minutes, something is wrong. Okay? So just restart it, try again. Okay? First group to finish, please give me your times. I'll try and summarize times up on the board so everybody gets an idea of roughly how long each experiment should take. Okay? Questions about the experiment? Calculations section and results. So for each experiment, or so for what I expect to see, I gotta actually write calculations on this. What I would expect to see in your results and calculations section would be a table very similar to this. For each trial, I only showed 3 here, I want to see a time value, concentration of iodide used, concentration of peroxide, and the rate for each trial. Sounds good? What is the concentration of iodide in each trial? Trick question, by the way. It changes. Why does it change? What happens to the volume? Volume changes. So to calculate your concentration of iodide, give you a quick idea on what's going on here. We know the amount of moles that we added in the course of the reaction, right? We know you added, let's say, trial 1. It says to add how many, what's the volume of, it's 2 volume. What was the volume of iodide added in trial 1? Someone say 2? I need a number. What's trial 1 supposed to be?
2 milliliters.
2 milliliters, so it was 2. So 2 milliliters of what concentration solution? .00. What was it?
0.3.
That was 0.3 moles of iodide per 1 liter. Okay, we've got volumes set up there, so we could potentially go through and cancel that out. We've got 1 liter is 1,000 milliliters, right? So that would give us the moles of iodide added per reaction. We want the molarity in the reaction. How do we get the molarity? It's moles per liter. There's our mole value. What's our liter value? How do we get the liter value? You'll take the total volume, which should be roughly 40 milliliters. Please do not just say it's 40. Do the calculation. And we'll make Excel do the calculation very, very swiftly for us. Okay? So you'll set it up where you'll get that volume. That needs to be in units of liters. So we could again go through and do our conversion. 1,000 milliliters is 1 liter. And we now have the concentration of iodine for trial 1. What's the concentration for trial 2? Pretty much the same thing, except this number may change. So we would then change that. Trial 3. Trial 4. Trial 5. 5 trials, all the exact same calculation. You could go through and do that by hand. Okay, so let's do a running tally of our hand calculations. So for our iodine, we had 5 calculations. What do we do for our peroxide concentration? We need moles per liter again. Do we know the molarity of the peroxide to start with? Do we know the volume we added? Do we know the total volume? Yeah. So to get our peroxide, we do another 5 calculations. doing the essentially exact same thing as this. Okay? Now we've got the rate. Our rate is going to be the concentration of iodine divided by time. So there's 5 more calculations. Okay? Except what's the concentration of iodine?
You said it was going to be the concentration of iodine divided by what?
Time for rate. What's the concentration of iodine though? Time is easy enough, that's already in our table. We have to determine it. Our concentration of iodine is related to what? The concentration of our thiosulfate. Okay? Our concentration of iodine at the end of our reaction is the concentration of thiosulfate, or very, very close to it. Okay? So what's the concentration of our thiosulfate? How much of that solution did we add? For trial 1 at least. Actually, they're all the same, aren't they? How much was it? 7? 5. 5 milliliters. We got our unit conversion. Okay, that gives us the moles of thiosulfate. We want volume, or sorry, molarity, so we'll do our total volume. Is the moles of thiosulfate equal to the moles of iodine? Let's phrase it another way. Does A equal B? Does the letter A look like the letter B? No. Okay, so we have to convert. How do we convert the moles of thiosulfate to the moles of iodine? We need the mole-to-mole ratio, which we get from our balanced equation. What was our relationship?
2 iodide.
Really? It was 2?
No, sorry, 2 thiosulfate for 1 iodide.
Our balanced equation says 1 mole of iodine is 2 moles of thiosulfate. We now know the concentration of iodine. We repeat that calculation 5 times, but wait, we didn't actually want the concentration of iodine. We wanted the rate for iodine. So we have to add up another 5 calculations on top of that. Just to generate this one chart, we have run ultimately the same calculation 20 times. Okay? Like I said, feel free to do it all by hand if you'd like. Okay? The next part of this is actually propagating to what we want to get out of it. Okay? So that gets us to what we've seen in lecture. We've got our concentrations and we've got our rates. How would we determine the orders for our reaction in lecture? Get tested on it on Monday, come on. We pick 2 experiments, and we would compare those 2 experiments. What would we be looking for? We'd be looking for, say, concentration to double, and see what happened to our rate. And we'd also pick, when our concentration doubles, that our concentration of the other species stays constant. Okay, so we don't have to worry about that, and we do that comparison. But to do that comparison, what do you assume? You assume that all of that data is perfect. And I know you guys are all wonderful people, but are you perfect when you cross through this door? No. So we need some way to account for that imperfection. So what we have to do is go through and solve for our orders in a different fashion. We must account for that error. So what we're going to end up doing, I don't remember how much information I gave here. What we're trying to do is solve for this rate expression. What we're going to do is pick some experiments very, very selectively. We're going to pick 3 experiments where our concentration of our iodide ion or peroxide, up to you, is relatively constant. Okay? That's going to simplify our rate expression. If our concentration doesn't change, is it going to affect our rate? No. So what we can do is simplify our rate expression to something along these lines. So in this case, I have assumed that the iodide concentration does not change. Okay? And when we've got our table, we'll be able to see which experiment our iodide concentration stays relatively constant. Okay? That means I get a new rate expression. Okay? The K in that case is no longer the same rate constant. Why? Because it doesn't take into consideration the effects of the iodide ion. So we end up generating a new rate constant. Okay? This equation on its own, do we know the rate constant? No. Do we know the order? No. Do we know the concentration of peroxide?
Yes.
Yeah, and we know our rate. Okay. We've got one equation, two unknowns. That's a bit difficult to solve. So somebody, thankfully, we didn't have to sit and stare at this for long enough to figure this out, or we didn't have to stare at it, went through and said, I'm going to try and manipulate the equation. I may not be able to directly solve it yet, but I'm going to see if I can manipulate it to get that Q into a more reasonable area to evaluate. So what I'm going to do is take the log of both sides. So I'm going to take the log of the rate, and that will be equal to the log of my peroxide rate constant, plus, and what we did here is pulled the Q down. Okay, remember, you guys remember that from lecture? We can pull that out. Times the log of peroxide. This equation is now massively important. What is special about this equation? It's a little bit of help here, kind of lead you into it. Let's give you some hints. Hint number 1. That help? Okay, well, let's try again. We have the equation of a straight line. Okay? So what we will do is plot the log of our rate on our y-axis versus the log of our concentration of peroxide on our x-axis. When we go through and tell our graphing program to plot that, we should see that our data points fall in a straight line, okay, or close to a straight line. They may not be perfectly in a straight line because our data isn't perfect. Okay? So what we'll now do is go back to our graphing program and say, graphing program, please, please, please fit a straight line to it. Ta-da, we get a straight line. Okay? So it slides a straight line through that data. What is the slope of that line? Q. What did we say Q was? The order with respect to the peroxide. We now know part of our rate equation. How do we solve for P? Same general idea, except now instead of picking 3 experiments where our iodide concentration stayed the same, we'll pick 3 experiments where our peroxide concentration stays the same. And we'll go through and generate a new plot. That new plot is going to give me a slope of a line. The slope of that line will now be P. That gets me pretty darn close to the overall rate law for this reaction. The one thing that I don't know yet, what's that? The rate constant. How can I solve for the rate constant? I've got all the orders. I can solve for the rate constant in every one of my experiments. We'll have to do it for each one. Why for each one? Our concentrations change, but what should happen to the rate constant? Should stay the same. So why do I have to do it for each one? Well, hopefully we don't have our temperature vary, but good call. to average out our experimental error. We don't know that any one of those trials is absolutely correct. So we'll calculate the rate constant for all trials. Then we can average our all trials to get a rate constant that should be much more accurate. Okay? So as far as our running tally, we had 20 calculations for basic stuff. We now need to calculate 5 more for our log of rate, 5 more for our log of concentration of peroxide, 5 more for our concentration of iodide. We're up to 35 calculations plus the graphs. Okay? We're really starting to push the limits of what you would be able to do by hand. Okay? This is just part 1. Okay? You'll go through and ultimately do almost all of these calculations again in part 2 next week. Okay? Questions about anything we've gone through and covered? Okay. Before we jump into lab, I know you're all itching to get in there and get started with this so you can get home and do all these calculations. Let's take a look at Excel. Okay. So, is that visible enough for you guys? If I try and jump the font size up? Yeah, jump it. Let's try 14. Is that better? All right, stick with 14. I'm not sure I'll be able to keep everything on there otherwise. Yes, no?
You maximize the screen.
I don't know that's going to help. Did that actually help you guys? I don't know. We'll try one more bump. Okay. So let's take a look at what we've got here. From your experiment, so we will highlight just your experimental stuff. I may regret doing this. If I make that green, can you still read it?
Yeah.
Okay. Experimental results. So everything in green is what you would get from your experiment. I picked a couple random times, and I put in the concentrations, your starting volumes, and you'll notice I also have some concentration information scattered up in that chart. Okay? So why did I format it this way? So we're going to have to use the volume data, and we don't want to put units on it because as soon as we attach units to it, Excel gets confused and now freaks out and doesn't know what to do with that number. Okay? So we've included these units in each column up at the very top, some information about the volume, okay, what that species is as well, and then the actual volume per trial underneath it. Okay? The next piece of information there, where it's important, I've included a concentration. Okay? So for the iodide, we need to know the concentration of the species. I pulled it out into a separate cell because if we go back to the calculations, remember we need to know the concentration. Okay? So if I leave it in this format, I can have Excel always refer back to that number without having to input it every single time. Okay? And we'll, like I said, we'll kind of go through this and show a couple things that can happen here. Total volume. That's going to be one of our first calculations. How can we determine the total volume? What do you have to do to get the total volume? You add all of your other volumes. So there's 2 ways we can do it. We can manually go through and say equals. So the first thing we do is hit equals, telling Excel, I want you to do a calculation. And I can now go through and click each cell. And you'll notice if you look up at the very top, I don't know how to get this bigger, unfortunately. If we look at the top up here, if you watch that area, that red circle is now going to disappear, but if you watch that area as I click, you'll notice it starts adding in some codes. What are those codes in reference to?
Cells.
The cells I'm clicking on. So it's now, we're telling Excel to add each of those individual cells. Okay? The other way to do it, which is my favorite because that I think just takes too long, so we can tell Excel, do a sum, click and drag. Return. Hey, the volume's 40. Okay? I want that calculation done for every single one of those experiments. So now what I can do is click on the cell that has my formula in it. Okay? And I want to tell Excel to repeat that calculation. I will move the cursor to the lower right-hand corner, which if you take a look at the cursor, you see it's kind of that white cross. Lower right-hand corner turns to a black cross. Click and drag downwards. It will now repeat the calculation, having adjusted the cell height. Okay? So now each of those sums has now been completed for me. Okay? Once I've got the formula in there, if I made a mistake in trial 4, I've got it left as blank. Well, that wasn't supposed to be blank. That was supposed to be 13.4. Whoa, cool. Did it for me already. How about the next one was actually supposed to be 78.269. That's not a 2, but close enough. Okay. It gives us that sum already. So it'll do the calculations immediately. Okay? Kind of makes sense? Next part of this. We wanted concentration of iodine. Let's not do that one yet because that one's a bit more difficult. Let's do the concentration of potassium iodide. What did you say, or what did we say that we had to do that calculation? We wrote it out. In theory, you've got good, careful notes that show exactly what you're supposed to do. What was your calculation? We took the concentration of iodine, so the first thing we'll start off with is an equal sign, because we want Excel to do a calculation for us. Equals, we said the concentration of our iodide. Remember how I set that iodide concentration out of the rest of the text? It's now saying to run the calculation with E4. Good deal. Okay, what do I do now? I multiply by the volume of that experiment, which happened to be E6. Fantastic. Now what do I do? So, I don't remember the calculation, how I got it shown. If you won't need the conversion factor, because the conversion factor, I think this is right. Because if you convert your starting volume, yeah, you don't need a conversion factor. Because your starting volume of potassium iodide is in milliliters, your total volume is in milliliters. Those two units would cancel. What would your leftover units be? Moles per liter from our initial molarity. Okay, so we don't need to include that conversion factor. If you want to, that's fine. It's just repetitive. You're gonna do it once, then you'll do the inverse of it in the next step. Okay? So the next thing to do would be to divide by our total volume. Where was our total volume? Hey, we calculated that already. Click, there we go. Now when we hit return, we now have the concentration of potassium iodide. Right? We want Excel to go through and calculate that for every single trial. How did we do that before? We went, clicked, and dragged. Okay? We're going to run into a slight issue here. Okay? Hopefully you notice in that second cell, so the last three we shouldn't really expect to see anything for because there aren't any numbers there. But in our second cell, we should see a number because we've got data points all the way across for that. And instead, it's saying value. Okay, why is it saying that?
Down a row in your concentration.
We move down a row. So when we do the calculations, okay, Excel, when we do that click and drag, will adjust according to how you've shifted or clicked and dragged. Since we clicked and dragged down, it's going to change every number down one unit. Okay? For some of the values, it makes sense. For our volume, we absolutely want it to shift down one because where did the volume go? Oh, the volume is down one cell. But what about the concentration that we started with? That stays the same. So what we have to do is tell Excel, don't touch that number. Leave that number constant. That cell happened to be E4, so we can go in and put a number or a money symbol in front of the E. Excel knows to now not touch E. That E value will always stay the same. regardless of where you click and drag. We also don't want it to change the number. It needs to always be E4. So what do? We put a money symbol in front of the 4 as well. Okay? Now when we click return, you notice we get the exact same number. Good, we didn't screw something up. But when we go back to click and drag, we now get a real number. Because now Excel is actually calculating appropriately. If you ever see that value thing show up, in fact anything like even the div 0 stuff, what you need to do is click on that cell wherever it's got a problem, and then you can click back on the formula part, which was up at the top. I remember, hopefully all this is visible when I close this. Okay, we can click back up on that formula. Once we click up there, Excel will highlight whatever your references are. Okay, so that you know exactly what they're referring to. So in this case, in that highlightation, what do we see? It's calculating E4, E7, and J7 in the calculation. So those things are now highlighted. We can see them. We know exactly what Excel is using to run the calculation. Okay? Kind of makes sense? Okay. We can then go through and repeat this. One thing you'll notice, once you've clicked up into that formula box, if you now start clicking through the rest of your file, you notice how I'm not actually clicking on an individual cell. It's inputting that into my equation, which means we have to get out of the equation format first. Usually if I end up getting into this trap, what I'll do is just hit return, which means it's going to do whatever calculation it was. Control Z will undo whatever stuff I did accidentally. Okay? Now I can go back to doing everything else. Concentration of peroxide was done very, very similarly. I just got to find it. We don't want it to change our concentration value. We'll multiply by the volume that we used, and we'll divide by our total volume. And we can click and drag. We get our concentrations. Concentration of iodine. How did we do our concentration of iodine? This one will be a little bit more complex. Let's kind of work it together. We said it was related to our thiosulfate, so we took the molarity of thiosulfate. Again, that's a reference that we do not want to change. We multiplied that by the volume of thiosulfate. Right? Then what we did is divided by our total volume, which gives us our molarity for thiosulfate. What did we want? Iodine. What was the next step to convert from thiosulfate to iodine? We need to divide by 2. Was it divide by 2? Yep. So we can either do divide by 2 if you want, or because I'm lazy, I'm going to multiply by 0.5. Okay, same thing, right? There we go. We now have the concentration of iodine. Click and drag. Yes? Okay. Next piece of information, we needed the rate. What did we say the rate was equal to? Iodine divided by time. Return. We don't need to do any money symbols in there. We want it to continue to do that calculation because the concentration and time will potentially change each time. Okay. To get our orders, we need the logs of all of these values. Okay. So the way I've got this set up is the log of Ki. So again, calculation, the log of Ki, close parentheses, again, click and drag, log of rate, click and drag. Okay? I could go through and do that for the log of H2O2, and you've noticed I've repeated the calculation for the log of rate. Okay, so just because that's there, I'll do it. Whoops. What happens if you don't put in an equal sign? It doesn't respond appropriately. Okay? So make sure you get that equal sign in there. Whoops, equals log rate. Okay. In this case, I can be extra fancy. Okay. Because I've got two cells highlighted, I can have it duplicate all the way down for both of them. Okay. The next part of this, once we had our log of all that information, what did we need to do? We needed to graph it to plot. What did we want to make sure we plotted? We wanted to make sure we picked experiments where only one concentration was changing. Based on the data that we've got here, the peroxide concentration does not change. So what I'm going to plot is the log of Ki and the log of rate. Okay? Because in that case, my concentration does change. So to go through and do this, since this file is already up there, you can take a look at it. You can click on that window, right-click, select data. You may have to add a series. Your window may look slightly different depending on which version you're using. You need an extra series in there. For me, I'd like to name it. I'd like to say this was for iodide order so that I can determine that. What do we plot on the x-axis? Go back to our equation. What did we say? It was the concentration, right? Oh, don't do that. If you ever make a mistake, just delete. Go back and fix it later. I want the log of concentrations on my x-axis. For my y-axis, I wanted the log of the rates. It's now entered that data. I can click OK, and you'll notice that we will see the equation of the straight line plot on there, or we'll see the line show up, okay, based on how I've got this set up. We want Excel to actually fit a trend line to this, so if you right-click on your data, add trend line, again, you may see a different window. We want to fit a linear equation. We would like to see the equation on the chart. For any lab where you have to write a discussion and conclusion, it would be important to also include the R squared value, which we'll talk about here in just a second. And we can click OK, and we now have the equation of a straight line. What would the order in this case be with respect to iodide? Can I make that bigger?
Yeah, Control K.
What's our order with respect to iodide? 0.152.
Yeah.
Okay. Yeah, not going to be a whole number. That's fine. Report it to 3 digits or 3 sig figs. That's going to be your order with respect to this reaction. We won't be able to get that whole number, but it should come out pretty close to it. Because we don't know for sure that it needs to be a whole number, leave it with the 3 sig figs. Okay? Run all your calculations assuming that. Okay? Almost done, I swear, and then, or unless you guys are just done and just want to do the experiment. What do you guys want to do?
Is there only one graph, or would have to like?
We would have to do the second graph, and in that case, you'd have to pick another 3 experiments where the concentration of iodide didn't change. I didn't plot or give you enough data to be able to do that. Okay. The last thing you'd need to do is calculate the rate constant. Your rate constant is going to be equal to, whoa, too far. Your rate divided by the concentration of your reactants to their orders. To get a superscript, it's the caret. So that would be shift 6, at least on my keyboard. In this case, we said it was 0.152 was the order, times the concentration of H2O2 to whatever its order is, just for the sake of argument, let's call it 1, and we'd get the rate constant. To repeat that calculation, again, click and drag, you've got the rate constants for all your experiments. Okay? All sorts of fun calculations that you can get Excel to do for you pretty quickly. Matter of what, half an hour to go through and do them all. Okay? I know that was a bit to go through, which is